The last video I uploaded showed my advancements of my own Hexapod robot. I covered the mechanical and electrical redesigns and some minor tests. The robot was able to move and even stand up by itself. This video covers the development of a remote to control the Hexapod, because I could only control it via USB and a serial terminal. A remote enables me to more precisely control the robot and do more complex movements overall. Before explaining how I designed the remote, I want to quickly go over the requirements. The first requirement is the Hexapod. A robot is required to test the remote, and since this is currently my only robot at hand, I need it for the tests. The next requirement is that I want 6 degrees of freedom and some buttons and switches to control the robot. More on this in a bit. If you want to replicate this remote, you will need a 3D printer, some ordered components and a soldering iron, as well as tools to crimp DuPont connectors. With the requirements covered, let's get to the design. Since some time I followed a channel called James Bruton on YouTube. This is also how I got inspired to build my own robot. James has a universal remote to control his robots and built an updated version for his OpenDog version 3 robot. I liked this design a lot, so this is why my own design is heavily based on it. A big thank you to James for making his designs publicly available. This enables people like me to use these files to modify and create our own devices. To follow his spirit, you can find all my designs and program files on my GitHub link below. To start off, the I/O needs to be defined. James' remote includes 2 joysticks with 3 degrees of freedom each. In addition, the remote has 4 buttons and 5 switches. It also has 5 LEDs to show states of the remote and/or the robot. Since I have no additions, I will use the same configuration of I/O for my own remote. I also like the overall form factor of James' remote, which is why my own design will look very similar. You can see the similarities here in the 3D models. As for powering the remote, James uses a USB power bank on the bottom of the remote. I didn't really like this approach, so I included some changes in my own design. Instead of using an external power bank, my remote includes a LiPo battery, a charge controller and a voltage converter. The remote can be charged via USB. To turn the remote on and off, a large switch is added in the front. With the general designs covered, let us move on to the wiring diagram next. You can see it here. Since the remote has a lot of I/O, this diagram contains a lot of connections. Let's start with the power supply. The LiPo battery is connected to a TP4056 charge controller to charge the battery. In parallel, the battery is also connected to an MT6308 step-up converter to get a 5V voltage. The connection between the battery and the converter is interrupted by a power switch. The resulting 5V power rail is connected to all remaining devices. Next, a Node MCU version 2 microcontroller has connections to an I2C bus to communicate with several devices. It is also connected to an nRF24L01 radio module for sending and receiving data. Via I2C, the microcontroller is connected with 2 ADS1115 analog-to-digital converter boards. Each of those is connected to a joystick, represented by the 3 single-axis joysticks. The joysticks also have buttons on them, which are connected to the last device on the I2C bus. Since the microcontroller has by no means enough I/O pins to connect to all remaining parts, an MCP23017 I2C I/O expander board is used. This board is connected to all buttons, switches and LEDs. For the LEDs, a 1 kΩ resistor is used each. Regarding the Hexapod, the server connections directly on the microcontroller need to be adjusted to allow the connection of another nRF24L01 radio module, as shown here. This is required so that the Hexapod can communicate with the remote. These are all designs for the hardware. Next up is the software. I originally planned to use the Wi-Fi module on the microcontroller for sending and receiving data. To get ahead of the tests shown later, I found out that this approach is by no means enough to quickly send and receive data for my use case. This is why the nRF24L01 is used instead. Of course, the remote needs a program to work, which will be now explained abstractly to avoid complexity. The remote starts by initializing all components. This includes the ADC boards for both joysticks, the I/O expander for LEDs, buttons and switches, and the radio module. The main loop itself isn't complicated. Each cycle it is checked whether a defined cycle time has passed. If true, the old timestamp is overwritten, all I/O is read, the data is sent via radio, and the LEDs are set. Because the joysticks are never perfectly centered, mapping their values to a desired range is a bit more complicated. For this, the value of the default joystick positions is averaged from 10 samples. This value is required to offset the 0 position and is called the reference position. Using this position and the minimum and maximum values of the target range, 2 linear equations interpolate between the old and the new range. The first equation starts at the minimum of the new range and stops at the reference position. The second equation starts at the reference position and stops at the maximum position. Linear interpolation using all 3 positions is used to correctly map the old values to the new ones. The remote scales all joystick values between -1024 and +1024, with the 0 being the default position. That's it for the design. Let me guide you through the realization process. First, I printed out the case of the remote. I then mounted all I/O in the case for a test fit. Next, I soldered a small PCB holding the charge controller and the voltage converter, as well as enough pins for power and I2C distribution. A quick test with everything wired up in the air showed that the devices work. I then moved all electrical components inside the remote and added the connections to the buttons, switches and LEDs. Closing the remote was quite challenging due to the amount of devices and cables. The result is a wired up and assembled remote. You might have noticed that the radio module is missing. This is because it came after first tests with the web server for data transfer. Anyway, I later added the radio module inside the remote. This made it even more difficult to close up the remote, but eventually it worked out. I created several programs for the remote, some for simple I/O tests, others more sophisticated to test the web server approach or to test the radio usage. Speaking of test programs, let's move on to the tests I did. The first test I did revolved around using a web server for the data transfer. I configured the web server so that buttons, switches, LEDs and joystick axes are grouped individually. The remote hosts the web server and the device accesses it as a client. When I tested the transmission speed, I got a cycle time of around 260 milliseconds. This would mean that less than 4 sets of data are transferred each second. For me, this is unacceptable since I want the robot to be responsive. To solve this issue, I followed the design of James Bruton and tested out nRF24L01 radio modules. These modules require defined sets of data packages that are sent or received. I first put every variable as a single value into the structure and tested out the transmission speed. I got a cycle time of under 1 millisecond, which corresponds to around 1000 sets of data each second. Just for fun, I tested how much I can improve the cycle time by optimizing the data structures. I combined the buttons, switches and LEDs into a single byte by setting each bit with the status of each device. This way I got the cycle time down to around 600 microseconds. Unfortunately, reality is often unforgiving. Taking the measurements of all I/O devices takes around 40 milliseconds, so I don't really benefit from this extreme cycle time. This is why I decided that a cycle time of 50 milliseconds is sufficient, corresponding to 20 sets of data each second. The last test I did was to demonstrate the usage of the remote to control the Hexapod. For this, I mapped 3 servos to each joystick separately. The switches allow to enable or disable the usage of all other legs except the first leg on the top left. As you can see here, the robot is quite responsive and moves its leg accordingly to my movements with the joysticks. I can even let the Hexapod stand up and wiggle around a bit, which I will count as its first proper steps. That was it for the tests. Let me conclude my findings. Here are the main takeaways from this video. A remote was designed, assembled and programmed based on the design of James Bruton. Tests showed that using a web server is insufficient for controlling a robot due to its poor cycle time. The usage of nRF24L01 radio chips enables a lot of data to be transferred between 2 devices. The cycle time was set to 50 milliseconds due to constraints caused by taking all I/O measurements. A final test demonstrates the usage of the remote to control the Hexapod. Before going over the next tasks, I quickly want to mention the costs involved in creating the remote. The total cost for all printed and bought components comes in to 133 euros, which is funnily more than the Hexapod itself. The total spent time sums up to 45 hours, 15 of that are for printing the case. As for the outlook, the next big task will revolve around the inverse kinematics of the Hexapod. This was already mentioned in the last video, so pretty much no updates regarding the next things to do. As usual, I took my sweet time to finish this little project. I started in March 2022 and finished it in February 2023. Most of the work was done in the first 2 and the last 2 weeks, with the rest of the time span no work being done at all. I also took a break of about 2 months starting in December, but now I am back and will work on my projects. Thank you as always for watching and see you in the next one.